Hello and welcome back. This is the second review video for Unit 4, Exponential and Logarithmic Functions. In the first video, just a reminder of what we did, just in case you want to review any of these, so you're going to go to the other video. We looked at the lesson overview and the Common Core standards associated with Unit 4. We defined exponential and log functions in terms of inverses of each other. We looked at how to convert between exponential and log form. We looked at the laws of exponents and logarithms and how they connected to each other. We took a look at fractional negative exponents, and we also looked at the basic graphs of exponential and log functions, domain and range, and asymptotes and such. In this video, we're going to continue by looking at how to find the equation of an exponential function given 2 points. We're going to look at Newton's law of cooling, which is an application of exponentials, solving exponential and log equations, compound interest formulas, interpreting and manipulating percents, and then we're going to sum up the most important information from Unit 4 at the end of the video. As a reminder, pause the video at any point that you need to write down anything you want to. To write the equation of an exponential form, all exponentials can be written in the form of a times b to the x. Okay, you can always translate them and stretch them in ways to get them into this form. So the goal of finding the equation of exponential form is to find what the a and the b values are. The a value in terms of its graph, that is the y-intercept. The b value represents how the graph is exponentially changing. Okay, it's going to be your base. It could be growth, it could be decay. Okay, but there are two cases for writing an equation. I'm going to look at the two basic cases. One's a little bit easier than the other. Now, in order to write the equation, you just need to know that it's exponential, and you need to know 2 points on the function. The 2 points can be given in a variety of ways. The 2 points can be given as 2 points. They can be obtained from a table. Or they could be obtained from a graph. So you can look at a graph and see where the graph intercepts on the coordinate grid, some integer points, or you can look at a table and get 2 points from there. Okay, either way, you need 2 points. There's two cases. The first case is the easy one, where 1 point is the y-intercept. And if you know the y-intercept, then you know the a value. Okay, so for instance, if I had the 2 points 0, 6 and 3, 20.25, and I'm asked to find the exponential function, notice because I have 1 point that has an exponent of 0, that's going to be the y-intercept. What really would help you is to rewrite these points into this form, okay? Because that's going to help you solve the equation. So if I put into y equals ab to the x form, I'm substituting the x and y coordinates in. So I get equations such as 6 is equal to a times b to the 0, and 20.25 is equal to a times b cubed. Essentially what I have is a system of 2 unknowns and 2 equations. 2 by 2. Now notice, as I mentioned, because 0, 6 is the y-intercept, and because b to the 0 is actually 1, that immediately tells me my a value is 6. Okay? That's the easy part of this one. So I really just have to plug a into the second equation to solve for b. So if I take that 20.25 equals a times b to the third, and I substitute that a of 6 in, I get the equation 20.25 is equal to 6 times b cubed. I'm going to solve that like any kind of equation. So the first step I would do is divide both sides by 6. And if I divide 20.25 by 6, that gives me 3.375 is equal to b cubed. Now when you want to solve an equation where you have the base raised to an exponential integer or fraction, whatever it may be, what you want to do is you want to eventually get into the form of b. just b to the first. And if you recall back to the properties in the laws of exponents, to make an exponent of 1, I have to find what multiplies to 3 to give me 1. And I'm going to raise that base up to the 1/3 power. Because if I raise it to the 1/3, 1/3 times 3 is 1. That's how I'm going to solve for b. So in my calculator, I'm going to raise 3.375 to the 1/3. And when you do so, make sure you put parentheses around the 1/3. You should get 1.5. If you didn't, keep playing around with it until you get 1.5. Now I have my a and I have my b value, so my equation for these 2 points, for the exponential form, is y equals 6 times 1.5 to the x. Now note, I could have also been asked to write it in the form f of x is equal to. Okay, it just depends on what the question is asking you to do. So just keep that in mind. Now to find an equation given 2 points without knowing the y-intercept, that's a little more complicated, but still not that much more work. Okay, again, we need to write down the 2 points that we have, so they could be given to us as points, or from a table, or obtained from the graph. So let's say I have the points 2, 144, and 4, 51.84. What I'm going to do is I'm going to write the 2 equations by substituting it into y equals a b to the x. So I'm going to write down the equations. 144 is equal to a times b squared, and 51.84 is equal to a times b to the 4th. That's my system of equations that I'm essentially solving. 2 equations, 2 unknowns. Now, unlike with the system of linear equations where you have to add them together in some way to eliminate a variable, the way we're going to eliminate a variable here, because a and b are being multiplied, is we're going to divide the expressions. So if I take ab to the 4th and divide it by ab squared, notice that will cancel the a's. And that's what you want to do. You want to eliminate one of the variables in some way. And I chose to put b to the 4th on the top because I want to have a positive exponent. It's a little bit easier to deal with positive exponents. You could have done ab squared over ab to the 4th, but I want to have a positive exponent. Now, because ab to the 4th is equivalent to 51.84, and ab squared is equivalent to 144, then that must be equivalent to 51.84 over 144. Simplify this further, so cancel the a's, so we end up getting b squared, because remember, it's dividing by the basis. It's the quotient property of exponents. We need to subtract the exponents. 4 minus 2 gives you 2. And if I do 51.84 divided by 144, that gives me 0.36. Now, b squared, you can take the square root of both sides. You can raise both sides to the 1/2. It means exactly the same thing, because it's fractional exponents. The denominator is the root, so square root. Square root or to the 1/2 power, either way you get a b value of 0.6. Now we know our b. We have to then use one of the original equations to solve for a. Doesn't matter which one you use. Okay. I might choose ab squared. Okay. Equals 144. So 144 is equal to ab squared. And I know that b is 0.6, so I'm going to plug that in. And I'm going to solve that for a, because then it's just a linear equation. 0.6 squared is 0.36, so I'm just going to move that in front of the a. Divide both sides by 0.36. I get a is equal to 400. I have my a, I have my b, I can write my equation. So y is equal to 400 times 0.6 to the x. Notice, again, I could also write it in the form of f of x is equal to 400 times 0.6 to the x. Depends on how the question is worded, if it's saying write in function notation or just an equation. Okay. That's how you solve for the exponential equation, given 2 points. Newton's law of cooling is one of the applications of exponential functions because if you have a large room, so notice these are typically in large rooms, then if you have an object that is at a different temperature than what the room temperature is, okay, so if it's above room temperature, typically if you take cookies out of the oven, they're going to be much warmer than the room temperature. They cool at an exponential rate. And the reason why it's a large room is because you want to have a fairly stable temperature in the room. If it's a smaller room, then you're going to affect the temperature of the room as well as it cools. Okay. We're dealing with large rooms. But the cooling is a big application of exponentials. So they're generally in the form f of t is equal to a times b to the t plus c. That's generally the form for Newton's law of cooling. You might see it in slightly different formats, but that's generally the idea. You have some exponential that is essentially shifted up vertically a certain number of units. Okay. And it's very important for you to be able to interpret the parts of the function. Okay. Now if we had y equals a times b to the x, just that, we know that a is the y-intercept. But you have to be careful about Newton's law of cooling because we're adding something to the function, which means that a is no longer just the y-intercept. It's just the y-intercept of that little piece, but it's being shifted up an additional c units. So the initial value of the y-intercept is always a plus c. Whatever the coefficient of the exponential piece is going to be, plus the vertical shift. The rate of decay, if you're having something that's cooling, you're going to have a b value that's less than 1. The rate of decay is therefore going to be found by doing 1 minus b. Okay? Because if you have a b value of less than 1, say you have 0.85 as b, you're not cooling at an 85% rate of decay. You are cooling actually at a 15% rate. Because this 0.85, whatever the base is in an exponential, it represents the percent remaining. Okay. So if you have 85% remaining, you decayed by 15%. You have to subtract it from 1 or 100%. Okay. The room temperature is just going to be your C value, the vertical shift, because they will cool. If you have cookies or if you have a meatloaf or whatever you're cooking, will cool to the temperature of the room. So it's going to go to that asymptote, which ends up being the vertical shift. So let me just put an example up here. Okay. So let's say I have the function f of t is equal to 115 times 0.86 to the t plus 65. Let's say I have that function to represent the cooling of something coming out of the oven. Okay. The y-intercept, or initial value, is going to be a plus c, which is the 115 plus 65. So the 180 degrees is where the temperature started at. Note, recall your knowledge about x-intercepts, y-intercepts, is that you can evaluate the function at t equals 0, which gives you the initial temperature, which hopefully you'll see that this right here becomes 1, so that's where the 115 plus 65 comes from. The rate of decay, the b value is 0.86, so it's 1 minus 0.86, so it's a 14% rate of decay, or 0.14, depending on how the question asks you to leave your answer. And the room temperature is just this value you're adding at the end, 65 degrees. Now the most common application of Newton's law of cooling is when things are cooling. However, if you brought something out of the freezer, for instance, you can also apply this as the Newton's law of heating. Okay, you just have to rework the b value so that it's exponential growth. Okay, that would look a little weird. Maybe your a value would be different, but anyways. Let's keep going. Solving exponential and log functions equations are going to be something that you really need to know how to do. Okay. And there's really three different ways to do this, using exponents and logs and the properties and such. The first two deal with solving exponential equations, and the last one deals with solving logarithmic equations. The easiest way to solve an exponential is to find a common base if you can. So that is going to be used when you have an equation such as this. 36 to the x minus 2 is equal to maybe 1 over 216 to the 6 minus 2x. The reason why common bases can be used here is because I can rewrite both bases as the same value raised to some kind of an exponent. I can change 36 into 6 squared. Again, I can change 216, well 216 is 6 cubed, so I can raise it to this negative third power because it's in the denominator. So I can write it with the same base of 6. I can then apply the power law of exponents to multiply the exponents to give me 6 to the 2x minus 4. A little better. 2x minus 4 is equal to 6 to the negative 18 plus 6x. It's a little larger for you. Negative 18 plus 6x. Now I have the same bases, so essentially what I could do to cancel out those bases of a 6 is I could evaluate both sides of the log base 6. Okay, log base 6 of 6 to the 2x minus 4 is equal to log base 6 of 6 to the negative 18 plus 6x. Now, most people skip that step because once you see that the same bases are there, the exponents must also be equal. Okay, but that's what this step actually ends up getting us to do. The log base 6's cancel with the 6's, so you have 2x minus 4 is equal to negative 18 plus 6x. A complicated exponential equation becomes a nice simple linear equation using this common and basis method. Now, they could end up being quadratics, okay, depends on what those exponents originally were. Okay, but this one ends up being a linear equation, which is easily solvable. So if most people, by the way, for this, once they get to this step right here, we'll just go right down to this step, and that's perfectly acceptable. You don't have to show the log base 6. But it's important to know the log base 6 of 6 is 1. Okay, they cancel each other. So I can solve this last equation further. The 2x minus 4 is equal to negative 18 plus 6x. Just like any linear equation. Subtract 2x from both sides gives you a 4x on the right. Add the 18 gives you a 14 on the left. Divide by 4 and reduce, I end up getting 7 halves. 14 over 4, which is 7 halves. If you aren't able to find a common base between the two exponential forms, or let's say we were only given the exponent is a variable in one of the sides, then you're going to use logs. Now, when I say use logs, you can use any kind of log your heart desires. You can use log base 10, which is the common log. You can use natural log. In my preference, I tend to go with the natural log because, as I mentioned, it seems more natural to me to do that. Okay, but you could use common logs because maybe that's the common way to do it for you. So let's say I have the equation 280 is equal to 20 times 2.72 to the x plus 40. Let's say I have that equation. That's an exponential equation because the variable that we're solving for is in the exponent. Now what I want to do, before I do anything with logs, is I got to get this expression, this exponential part, by itself. I have to get that by itself. So I have to apply the rules of algebra, subtracting the 40 from both sides, divided by 20 and so forth, until it gets by itself. So if I subtract 40 from both sides, I get 240 is equal to 20 times 2.72 to the x. Divides both sides by 20, I get 12 is equal to 2.72 to the x. Regardless of how your original form is written, you want to get it so that the exponential piece is completely by itself. So just manipulate the equation until you get there. Once it is by itself, then you can take the log of both sides. I'm going to choose natural logs. So natural log of 12 is equal to natural log of 2.72 to the x. And one of the reasons why we take the natural log of both sides is because one of the properties of logs saying that if we have something raised to a power, that exponent goes right out front. It moves that x from being an exponent to being part of a multiplication. And then notice to solve for x, we just divide both sides by natural log of 2.72. So x is natural log of 12 divided by natural log of 2.72. And you just got to type that in your calculator. In doing so, gives you the value of 2.483337478 ... And depending on how the question asks you to round your answer, nearest tenth would be 2.5, hundredth would be 2.48, thousandths would be 2.483, and so forth. Okay. That's how you solve exponential equations. Now, just as a side note, is if you decide to do common logs instead, you would have had log of 12 divided by log of 2.72. So your equation would be exactly the same in solving, except instead of a natural log, you'd have a log written. And notice if you type that in your calculator, you'll get the exact same value. To solve logarithmic equations, what we're going to do is we're going to convert them to the exponential form. Okay, so if I had an equation such as 3 is equal to the log base 7 of x plus 3, I'm going to first convert that to the exponential form. So remember, the base is 7, the exponent is 3, so it's going to be 7 to the third is equal to x plus 3. And then just solve it like you would any kind of an equation after that point. I got that backwards. 343 is equal to x plus 3. Subtract 3, you get x is equal to 340. Done. Something that looks really complicated can very easily become like something that's so simple. Now, in solving these exponential and log equations, if you notice you're dealing with anything like e, you are definitely going to use natural log. Or if you see natural log in an equation, you're going to use e. Okay. So keep that in mind. Okay, now let's look at the compound interest formulas. These have a lot of applications in terms of radioactive decay, investing money into an account, and so forth. Okay, there's two different formulas. One is if you're compounding over equal intervals, and one is if you're compounding continuously. Both could be either growth or decay. Okay, but most commonly they are growth for the first one. Okay, this is where you have a is equal to p times 1 plus r over n to the n t. One thing to note about these formulas is that t is always in years. Okay. So when it's compounded over equal intervals, you're in terms of how many intervals over the course of a year. So the most common ones you will see are compounded quarterly. That's going to be n is equal to 4, because 4 times a year. And another one you're going to see is monthly. That's another common one. That's compounding 12 times. Weekly, 52 weeks in a year, so n is 52. And daily is another common one. That's 365 days a year. unless you happen to be in a leap year. Then if you want to use 366, I suppose that's fine, but 365 is typically what's used. Now notice, there aren't exactly 52 weeks in a year. There aren't exactly 365 days in a year all the time. There aren't exactly the same number of days in each quarter or the same number of days in each month. But that's just how the interest is being broken up. So the nominal rate, by the way, I'm going to just talk about this below, is in name only. It's a rate in name only. So the R value that's going to be given to you is going to be the yearly rate. Now if you're compounding over equal intervals, what you're really doing is you're dividing that rate into each, into as many times as you're compounding it. So if you're doing quarterly, you just divide, say you have a 24% rate. If you divide that by 4, that means you have 0.06. Okay, so that means in the first quarter you have 0.06 interest, second quarter 0.06 interest, third quarter 0.06 interest, and the fourth quarter. So over the course of the entire year, you split that 0.24, that 24% interest, into 4 equal parts. What that ends up doing is at the end of the year, that's not actually the interest you actually earn. You actually earn a little bit more, which is really nice about these exponential equations. Okay. You don't actually, over the course of a year, if you compound quarterly, monthly, weekly, or daily, earn 6% yearly interest. The effective rates for the compounded over equal amounts is going to be found by doing 1 plus r over n to the n. That's going to be the effective rate. Okay. So using the 24% as an example, if I do quarterly, I'm going to evaluate this. Okay, notice you always have to convert that into a decimal. Okay, and notice that if you type in your calculator, you get 1.26247696, and so forth. Okay, ... Over the course of one whole year, then, you actually have a 26.25% increase. Okay, not the 24%, because exponential increases each increment. So it gets a little bit larger at each increment that you're evaluating. Okay. So that 24% interest that you're given as a rate is only a name only, and you're dividing it equally over the quarters, or the months, or the weeks. Okay. Just a little word about that. Okay. Now, notice if you get larger and larger in the number of intervals you have, so you have 365 for daily, say you want to do hourly, or minutely, or secondly, then you approach something called continuously. So continuously compounding is essentially where you have n is equal to infinity. Now infinity, as you recall, is not a number, it's a concept. But that's just saying, well, what happens if you instantaneously compound your interest? What happens? It turns out that this value, 1 plus r over n to the n, as n gets larger and larger and larger, that approaches the value e. That's where this number really comes from. It's the most common application of e. So continuously compounding interest is going to be found by using the formula p is equal to e to the r t. Sorry, e to the r. That's what it comes up to. Okay, a is equal to p to the e to the rt. Now, if you're talking about so again, if you were having a 24% rate, yearly rate, compounded continuously, then that's only a name only. The effective would be e to the r. That's the effective rate for continuously compounding. Note, because continuously is instantaneous, that's as high as an n value you're going to get. This is also considered the maximum effective rate. Okay. So if you're given a yearly rate of 2.72% and you want to know what is the maximum effective rate that you're actually going to get, just raise e to the convert it to a decimal value of r. Now note, with any of these things that we're doing in this review video in this unit, you could be solving for any variable. So you could be solving for the principal amount, you could be solving for the rate, you could be solving for the time, so you're just going to be solving an equation like we did in the last slide. So you may have to use logarithms, you may have to use common bases and so forth. Okay, let's look at percent manipulations. Okay. Now, sometimes you're going to be given a situation where we're given the percent rate for a certain period of time, and you're asked to find the percent rate for a different period of time. So for instance, let's say that if you know after 6 years is the 15% growth rate, what is the growth rate after 10 years? So we got to manipulate that 15% to find out the growth rate for 10 years. And to do that, what you have to do is you have to find first what is the growth rate per year. Now this is going to relate to fractional exponents. Okay, so if I have some base raised to the x over y, a fractional exponent, this numerator is the power, and this denominator is the root. Now remember, powers as integers always make things larger. Roots as integers make things smaller. So if I want to go to 1 year from 6 years, I have to take a root. So I'm going to raise the 1.15. By the way, because it's growth, it's going to be 1 plus the 0.15. That's where the 1.15 comes from. The growth rate is 15, so it's 1.15 to the 1/6 power. That'll give me my yearly growth. I have to go backwards, take the root. So from that yearly growth, I can then go to the 10-year mark by raising it to the 10th power. So 1/6 to the 10th power, which essentially is 1.15 to the 10/6. That's the 10-year growth. So I have to evaluate what 1.15 to the 10/6 gives me. And typing that in my calculator, I get 1.26230141. That's a little messy. Let me redo that again. 1.26230141. So essentially over 10 years, I have a 26.23% growth after 10 years. When dealing with decay, you have to be careful about one thing. Okay, decay is 15% decay. It's going to be found by 1 minus 0.15. Okay, so you have to convert that into 85% remaining. And because after 6 years is a 15% decay, I have to raise that 0.85 up to 1/6 to get my yearly decay. Which means if I want to find after 10 years, I have to raise that 1/6 to the 10th power to give me 0.85 to the 10/6. So evaluating that, 0.85 to the 10/6, that gives me approximately 0.7627195462. Now note, that is going to be the percent remaining, so that doesn't give us right away the rate of decay after 10 years. I have to go back and do 1 minus at 0.762719 ... to get me my rate of decay, which is going to be 0.23728043838. Okay. So my rate of decay over 10 years is approximately 23.73% decay after 10 years. That's how much it goes down from 100%. Alright, now the most common application of this problem deals with half-lives. Half-life problems are very common, especially in science, in chemistry and such. If I say that an element takes 25 years to reach its half-life, that means half of it's going to remain after 25 years to find its yearly decrease in amount. I have to raise 0.5 to the 25th power. 1 over 25th power. That will give me my yearly decay rate. And let's say I want to know how much is going to remain after 50 years. Okay. Then essentially what I'm doing, then I'm evaluating 0.5 to the 50 over 25. Or if I want to know how much is remaining after 17 years, I'm going to raise it to the 17 over 25, and so forth. And if I want to know the rate of decay, then I have to do that 1 minus whatever I get. Okay, so that's just a very common application of percent manipulations. Okay, so let's sum up the results from these 2 review videos and the most important information that you've learned. Okay. These are all things you should be able to do at the end of this unit. Now, there's a lot packed in here, so keep that in mind. But in general, you should be able to understand that exponential and log functions are inverses of each other. Okay, that they're inverses of each other. You should be able to apply the properties of exponents and logs, by the product, the quotient, the power rules. You should be able to convert between exponential and logarithmic form. Okay. If you're given an exponential, you should be able to find the logarithmic equivalency. Given the log form, you should be able to find the exponential equivalency. You should be able to graph an exponential function or a log function, knowing the domain range, the rate of growth or decay, which is your p-value, the y-intercept, and whatever asymptote is there. And we're going to be focusing a little bit more on this in the transformations unit in a future review video, but it's important to know the parent functions. You should be able to find the equation of an exponential function given any 2 points, or its graph, or its table. You should be able to solve an exponential or a logarithmic equation. Apply the compound interest formulas to find a missing variable, so you'd be finding the time it takes to get to a certain amount, could be, so you're going to solve using logarithms, or it could be finding the amount after a certain amount of years. Should be able to interpret and manipulate exponential expression to find any amount. Okay, so that's that manipulation of percents. And Newton's law of cooling. Okay, be able to apply it and interpret the parts of the equation to find different pieces of information of the problem. Thank you for watching this video, and I hope to see you in the next video. Thank you.